Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on modeling heteroskedacity. And in this lesson, I'll introduce one of the simplest time series model to model the conditional variance, so-called the arch model. Let's assume we begin with fitting an ARMA model to a time series YT as provided on a slide, where the residual process is ZT assumed to be white noise with constant variance given by sigma squared. However, in many applications, the time series data often exhibit volatility clustering, where time series show periods of high volatility and periods of low volatility, indicating non-constant variance. If such, we can rewrite the error term ZT as the product between a deterministic but time-varying component, sigma t, and a random process RT with mean 0 and variance 1. In this lecture, we'll focus on modeling the volatility sigma t. We'll begin with one of the simplest time series models introduced by Robert Engel in 1982, the auto-regressive conditional heteroskedacity, or in short, ARCH model, used to model the time-varying volatility often observed in economical time series data. For this contribution, he won the 2003 Nobel Prize in Economics. ARCH models assume the variance of the current error term or innovation to be a function of the actual sizes of the previous time period's error terms. Often the variance is related to the square root of the previous innovations or error terms. The ARCH family of models assume that the volatility, or sigma t squared, is a linear function with lagged values of the mean equation errors zt. Thus, the time series dynamic of volatility is like an AR process. Specifically, the squared errors zt are modeled using an AR process where gamma 0, gamma 1, and so on are the error coefficients at omega t. And omega t is the error assumed to be uncorrelated with mean 0 and variance lambda squared. The expectation of zt squared given past history of the error process is equal to the error polynomial for zt squared. But the expectation of zt squared is also equal to sigma t squared. Hence, we model the condition of variance as a linear combination of past squared error terms, gamma 0 plus gamma 1 times zt minus 1 squared plus gamma 2 times zt minus 2 squared, and so on. In the introductory statistics courses, it is often mentioned that independence implies zero correlation, but not vice versa. A process, such as the ARCH process, where the conditional mean is constant but the conditional variance is non-constant, is an example of uncorrelated but dependent process. The dependence of the conditional variance on the past causes a process to be dependent. Thus, in ARCH models, the conditional variance has a structure very similar to the structure of the conditional expectation in an AR model. I explained this concept with the simplest ARCH model, ARCH of order 1. We'll consider here YT to be the mean, which does not vary in time, to be a process with a mean which does not vary in time, plus the ZT process, which is modeled using an ARCH1 model. That is, the conditional variance is equal to gamma 0 plus gamma 1 ZT minus 1 squared. Note that sigma t is assumed deterministic. The best CT are assumed given and hence realized at time t. However, we do not observe volatility with certainty. The true volatility of ZT is sigma t squared, which is deterministic, plus omega t, which is random, where omega t has mean 0 and variance 1. Those two processes are also assumed uncorrelated. Together, this leads to the AR1 equation for ZT, squared as provided on the slide. This equation is crucial in understanding how arch processes work. If zt minus 1 has an unusually large absolute value, then sigma t is larger than usual, and so zt is also expected to have an unusually large magnitude. This volatility propagates since when zt has a large deviation that makes sigma t plus 1 squared large, so that zt plus 1 tends to be large, and so on. Similarly, if zt minus 1 squared is unusually small, then sigma t squared is small, and zt squared is also expected to be small, and so forth. Because of this behavior, unusual volatility in zt tends to persist throughout, but not forever. Because of the characterization of zt squared as an AR process, we can further obtain the conditions of stationarity of the arch model for a time series yt. The conditions are as follows. The unconditional expectation of the time series is mu. The unconditional variance of yt is the variance of zt squared, which can be shown to be equal to gamma 0 divided by 1 minus gamma 1, where gamma 0 and gamma 1 are the AR1 coefficients for zt squared. We also need to have that yt and hence zt are uncorrelated, because we assume that the variance is finite and positive under stationarity. Thus, gamma 1 needs to be smaller than 1. These are the conditions under the so-called weak stationarity. In order to ensure strong stationarity, we need to impose additional constraints on gamma 1 for ensuring that the fourth moment of zt is finite. The fourth moment, assuming normality, is provided on the slide. In order for this to be finite, we also need to impose the additional constraint that 3 times gamma 1 squared is smaller than 1. This is needed in the derivation of the quartuses, which is a measure of how fat the tails are. The quartuses of the arch-1 model under the assumption of stationarity is larger than 3, which means that an arch-1 model for zt has fat tails, and thus it is more likely to produce outliers than the simple normal white noise. This is a comparison of the distribution of distributions with different quartuses. For distribution with quartuses larger than 3, as the one in the middle, the curvature is high in the middle of the distribution and tails are fatter than those of a normal distribution provided on the right. A distribution of data with fat tails is frequently observed in financial markets. We can combine the arch model with an ARMA model as illustrated in the first slide of this lesson. Some specific examples are provided here. We can begin by assuming an AR1 process for modeling yt with mean mu and AR coefficient phi. Then the AR process zt can be assumed to be an arch1 model. Hence, the conditional variance is gamma 0 plus gamma 1 times zt minus 1 squared. A second example provided in this slide is the ARMA 1-1 and arch2 models, where yt is modeled by an ARMA 1-1 with zt, the error process, being modeled by an arch2 model. Hence, the conditional variance is gamma 0 plus gamma 1 times zt minus 1 squared plus gamma 2 times zt minus 2 squared. It's important to note that when we have joint models, as provided here on this slide, we need to estimate them jointly. It's not good practice to first estimate the ARMA process for yt, then to apply an arch model to the residual process. We will discuss this aspect with a data example in a different lesson. How to estimate the arch coefficients or the arch model? The common approach is using the maximum likelihood estimation. Because the time series yt is not, the variables in the time series yt are not independent, then the likelihood function cannot be written as the product of the individual marginal distributions of YT. Instead, it needs to be decomposed as the product of conditional distributions. I'm introducing here the concept of conditional likelihood, as discussed in the first lecture on this course, reviewing essential concepts in statistics such as the decomposition of the joint distribution. We can decompose the joint distribution of the random variables yt minus 1 up to y1, modeled by an RP model using the unconditional likelihood as defined on the slide. The second term in the decomposition is a joint distribution of the first p random variables in the time series. Except for the small order arch models, this last term is difficult to express and therefore ignored if p is much smaller than t. Thus, in fitting an arch p model, we instead maximize the conditional likelihood defined on the slide. The maximization is with respect to the AR coefficients in the arch model. Since the estimation requires a numeric algorithm, it is only done using a statistical software such as R. In summary, in this lesson, I introduced one of the simplest models used to model the conditional variance or the heteroskedacity in a time series, the so-called arch model. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm associate professor in the Stuart School of Industrial and System Engineering. This lecture is on modeling heteroskedasticity in a time series. And in this lesson, I'll focus on a specific data example for illustrating the arch model. We'll return to the data example in which we will model the stock price of a company. I selected here a company with very large volatility, PDCE Energy, which is a crude oil and natural gas producer with headquarters in Denver, Colorado. Daily stock price for more than 10 years of data starting with January 2007 is considered in this data example. The reason for being interested in estimating the volatility for this stock price is because it is highly dependent on the crude oil price. In the lecture for ARMA modeling, we learned that we can identify the order of an AR process using the PACF plot. Since ARCH is an AR process for the squared ZT process or the squared residual process, we can use the PACF plot to identify the AR order of the ARCH model. Thus, in this example, I use the R command PACF with the input the squared residual process. And this is the PACF plot. From this plot, we see that the PACF is large for the first 7 orders, but decreases afterwards. However, there are still some large PACF values outside of the confidence band for large orders. Using this approach, we may select an order equal to 7 as fitted in the command on this slide using the CARCH-R command. In this command, we input the process to be modeled, in this case the residual process, and the order for the arch model. Please pay attention to on how the arch order is specified in this arch command. We'll see other implementations of arch and GARCH models where the order is specified differently. Last, we evaluate the goodness of fit of the arch fit by first obtaining the residuals from the arch model. Note that I remove the first 7 values from the residual vectors since there will be NAs. This is because we fit an arch model of order 7. I plotted here the ACF of the residuals and of the squared residuals from the arch model to check whether the residuals are uncorrelated and whether there is an arch effect left in the residuals. To complement this analysis, I also applied the hypothesis testing procedure, Lewin box for testing for serial correlation and arch effect in the residuals. The input lag equal to 8 and fit df equals to 0 is because we applied the test to residuals derived from a model with 7 coefficients. The output of the arch fit is here. It is similar to that of an AR fit. The output provides the estimated AR coefficients along with inference on statistical significance of the AR coefficients. According to this output, all coefficients are statistically significant, hence an order of 7 is appropriate. The output also provides the results from a hypothesis testing procedure of uncorrelated residuals and for an arch effect in the residuals. According to this test, we reject the null hypothesis of uncorrelated residuals, but do not reject the null of an arch effect in the residuals. Applying the box-Lewin test, we have some evidence to reject the null hypothesis for both tests, and the p-values are both small, although not smaller than 0.01. Given this level of p-values, we reject the null hypothesis at the significance level 0.05, but not at the significance level 0.01. The ACF plots, on the other hand, look like those of white noise, since the ACF values are within the confidence band except for the lag 0. I will note here that there are other R packages to fit arch and more generally Garch models, which will be discussed in other lessons in this lecture. Two such implementations are using the Garch function from TCA package, and a second implementation is the Garch fit function from the F-Garch package. The Garch function from time series package is fast, but does not always find solutions. The Garch fit function from F-Garch package is slower, but does converge more consistently. So far, I illustrated the implementation using the Garch function in a T-series library. This slide also presents the implementation using the Garch fit function. We can fit the ARMA-Garch model using the Garch fit function in two ways. One is to fit an ARMA process on the time series first, then model the residuals from the ARMA fit using an arch model. However, this approach does not provide efficient estimates for the ARMA arch joint model, not as efficient as the one when we estimate the two models simultaneously. We can also fit an arch model using the Garch fit function by specifying the orders of the ARMA model through the option ARMA plus the orders of the arch model for specified by the Garch option. Note that for this implementation, the first order is for the AR part of the model, and thus we specify Garch 70. This is different from the implementation using the Garch R function in the time series library, where we specify Garch 07. This slide compares the outputs for fitting the arch model to the residual process using the two implementations, using the Garch function on the left and the Garch fit function on the right. The omega coefficient in the Garch fit corresponds to the A0 coefficient in the Garch. The coefficients alpha 1 to 7 correspond to the coefficients A1 to A7. The estimate from the two models are almost identical. The difference between the output is that the Garch fit function also provides the estimate for the mean of the fitted process, the mu parameter. In this case, the mean parameter mu is not statistically the estimate of the mean parameter mu is not statistically significant. This is not surprising since we applied the arch model on the residuals of an ARMA fit. Based on this output, the fitted arch model is provided here on the slide. This is the output from the joint modeling of ARMA and arch applied to the time series of the return stock price using the Garch fit function in R. The fitted model, as provided by this output, is provided here on the right. The first part of the output is for the ARMA model, the estimated ARMA coefficients. Hence, the output is different from the output of the arch fit using the residual process. In fact, comparing the estimates from the ARMA process that we initially estimated with disregarding the arch portion of the model, when we comparing those to the estimated coefficients using the joint ARMA arch model, we find that the estimated ARMA coefficients from the ARMA arch fit, the joint ARMA arch model, are different from the estimated coefficients of the ARMA fit alone. On the other hand, if we compare the arch fitted model using the ARMA arch fit versus the one fitted in the previous slide, where we fitted the arch model on the residuals, the fitted models are similar. In summary, in this lesson, I provided a data example to illustrate how to fit an arch model. Thank you.